determining whether or not we have unstable systems or not. And this is one of the problems that they were faced with when they were doing these analysis. Nyquist was actually faced with these systems that people saw in practice first. That they applied feedback. Initially, with very little feedback, it was unstable. It was stable, and then as they applied more feedback, it became unstable. And then these systems became more stable again, with applying even more feedback. And people were scratching their heads and saying, what's going on, right? And he basically said, went back mathematically, looked at it, and said, well, okay, what is really going on, and what are the criteria? So to do that, we really need to come up with what's called the Nyquist Criterion. And what I'm going to do for you, do here, is that basically I'm going to derive the Nyquist Criterion for you. But this is not. This is a more, hopefully, a more intuitive derivation than a regular derivation. So think about it this. So let's say I am interested in this. I'm interested in the complex plane, right? So let's say my variable, my complex variable s, can go through some trajectory in the space. So this space. So let's say this is the real and imaginary value of the s. Let's say S goes through some contour, some closed contour C1. So let's say it's going through some trajectory. And the only constraint on it is that it's closed. And let's say in this plane, so this is basically contour C1. And let's say we are interested in some function, some complex function of S. Let's say f of S. This is the S plane, this is the f of S plane. So I'm showing here the real and imaginary part of f of S. Now, as S goes through this trajectory, right, f of S goes through another trajectory, evaluated for those values. So for this value of S, I calculate f, it's some value here, or another value I calculate is some other value, and it goes through. And if it goes back, if S goes back to the same value, meaning that this is a closed trajectory, this guy has to be a closed trajectory. Okay? Because it's going to the same value. Eventually you're evaluating for the same value, it should be the same. It's a function. So now let's say f of S has some poles and zeros. So it has some, it's a polynomial function with some poles and zeros. So let's look at those poles and zeros here. Let's just for the sake of argument, I'm just showing 3 of them. But there could be n poles and zeros. Right. Now, at a given point here, and a given which corresponds to this point here, if I ask you, what is the angle of f of S? What can you say? So, what is f of S? F of S really is some constant times, let's say, some constant a0 times s minus z1, s minus z2, all the way to s minus zn, divided by s minus p1, s minus p2, all the way to s minus pn. Right? So if I ask you what's the magnitude and you can write this in terms of magnitude and phase. So you can write it as saying, okay, this is the magnitude of all of these terms at any frequencies. So let's call it the magnitude of f of s. And then times e to the j phase of f of s. Right? Now, what is the phase of f of s? Do you agree that it's the phase of all of these numerators minus the phase of all the denominator terms at any given point? Right? It's an exponential, right? Just basically, what you can say is that the phase of f of s is going to be the sum of all the, let's say, just to keep consistency, theta for, okay, phi for the pole, so, and theta for 0. So phase of all the zeros, so theta 1 plus theta 2 plus theta n, which basically theta 1 is the phase angle of this vector, s minus z1. This is the phase angle of s minus z2, and so on and so forth, minus phi1 plus phi2 all the way to phi n, where phis are the phase angles of s minus p's. And these are complex quantities in general. that it says that the phase angle here, this angle, at any given point, so this is the angle of f of s, right, is the sum of these angles, let's say that point, let's say, corresponds to this point. This is theta 1 minus these angles. Let's say this is phi 2, and this one is an angle like that. This is phi 1. Right? The angles of these vectors from poles and zeros to that point S. This is the point S. These angles, that's what I'm calculating. It's the difference of these two vectors, right? It's the difference of this vector and that vector. S is this vector minus Z1, which is this vector. Gives you that vector. So these angles are the sum of the thetas minus the sum of the phis is that angle. Do you agree with that? So now, if I basically, if I don't encircle any poles or zeros here, let's say if I go around here and there's no poles or zeros within this contour, do you agree that this vector will go around and come back but cannot encircle the origin? Let's think about it. If there are no poles and zeros inside, each one of these angles increases and then decreases. Eventually goes back to the same value, right? This guy goes up. First, let's look at it as it moves. Oh, it's moving this way, doesn't it? Okay, so it goes down, this angle goes down, goes back up, goes down, comes back here. Every single one. As long as none of them are inside, this guy also will go and come back, but it can't encircle the origin. Because if it were encircling the origin, let's then just do something else. So let's say I pick another contour where I am doing this. Then this guy will have to encircle the origin. But let's just pick one. If this was my new contour, then if I go through this contour from the perspective of this pole, I am going one full circle. So I have 2 pi, right? Therefore, this guy has to go 2 pi. So this has to encircle the origin. So the number of times this contour encircles the origin tells you how many, it shows it's a function. It basically is the number of times it encircles the origin is equal to the number of zeros minus the number of poles that are inside this. Agreed? So let's write that down. So we say the number of times encirclements here is equal to the number of zeros minus number of poles in the function f of s. Everyone agrees with this? This is intuitively clear from this, right? Yeah.
Is it number of zeros and minus number of poles within the contour, right?
Within the contour. Within the selected contour. For a given contour. See, the only thing you choose is this contour. Once you choose this contour is known.
Yeah.
It's already determined by the function. So if you have a given function, once you pick a contour here, it gives you a contour there. I'm saying that if you look at this contour, if I show you something like this, you can tell me that what? It's going counterclockwise, essentially. So it's basically showing me I have one more zero than one less zero than one pole inside. So it says I have one more pole than zeros. So actually, you know what? I actually got my contour directions. Well, you can do it this way, but let's keep it consistent. Let's change the direction of the contour this way to make it consistent. So Now, what happens is that here, for instance, if you had something like that, then it would correspond to one counterclockwise term, which means that I have one, it's minus one term, right? Because it's going counterclockwise. So it's basically I have one more pole than I have zeros. That's all it tells me. Fine? Okay. So this is called Cauchy's principle. Cauchy's principle says the number of is basically the number of encirclements is the number of zeros minus the number of poles of that function. So how do we use this for stability analysis? So now, what am I interested in is this function, right? I want to know if this function has roots in the right half plane. But what can I say about this function? I can say, actually let's think about it. This function has a numerator and a denominator. So you can write it like this. So you can see that the poles of this function are the same as the poles of the t itself. So if we assume that we have no, basically whatever poles that is, for this one, you will have the same. The only thing that's different for this is the zeros, the numerator of that. Now, for determining whether or not, so what's the objective? The objective is to determine whether or not we have the right half plane poles. So to do that, I have to pick a good contour, right? I have to pick the right contour to determine that. What is that contour? So this is the C1 contour in the S plane. So I'm interested in this entire right half plane. So I can choose my contour to be this whole thing. Going to infinity, coming back from infinity, and then coming from minus infinity. Going this way. If I choose my contour to be that, then if I have anything in there, it will show up. Okay. So for that contour to apply, so what do we need to do? We say basically, I want to see what happens to the contour of f of s. So this is imaginary of f, and this is the real of f of s. Now, let's say this contour goes like this. Let's say I just pick an example. So you start from minus infinity, and then it goes like this. If it doesn't encircle the origin, in this case it hasn't encircled the origin, right? What does it tell you?
It has or hasn't?
It has not, right? This is the origin. Right. Then it means
number of poles has the equal number of zeros.
the number of poles is equal to the number of zeros. Of what?
Inside the.
Okay, exactly. So the number of poles of 1 plus t of s is equal to the number of zeros. But I know what do I know about the poles of t of s? If I start with a system, let's assume that you start with a system whose loop gate is stable. Right? Which is a reasonable assumption. If you get a loop gain, if you start calculating your loop gain, and you see that your loop gain already has right half plane poles, then the rest of the analysis is kind of moot, right? Agree? So for us to have a meaningful question to ask, first we have to assume that the open loop system is stable. Loop gain is the gain of the open loop system, right? We've opened the loop. So the loop, so we know that basically this was basically written as numerator plus the denominator of s divided by the denominator of s. So we know the roots of this are the same as the poles of this are the same as the poles of t of s. And we know that t of s doesn't have any right half plane poles. So if we evaluate this function, all we get is something about the number of its zeros or roots. Right? Because we start with the assumption that there are no right half, so we are assuming that there's no right half plane poles in t of s, which is a reasonable assumption. If you make that assumption, It means that there are no poles in this transfer function here. The only thing that got is zeros. So the number of encirclements will give you the number of right half plane roots of 1 plus T of S. Correct? Agreed? So if you know that, then you basically, all it says is that look how many times it encircles the origin, and that tells you how many right half plane roots you have for this, which is what matters, right? Because this is in the denominator of the transfer function. So the number of right half plane roots of this gives you the number of right half plane poles of the transfer function, of the closed loop transfer function. Agree? But you don't have to write any integrals to arrive at this result. So now the way you do it basically is that since this is the function 1 plus t, so instead of looking at function 1 plus t encircling the origin, I can say I can shift everything by minus 1. So it's equivalent of saying that function t of s should not encircle point minus 1. So everything will get shifted. It's like everything is shifted by 1. So instead of evaluating 1 plus T of S, which is what this is, if I evaluate T of S in the complex plane, so this is real of T of S, this is the imaginary of T of S, then I can basically look to see if it encircles point minus 1. And if it does, the number of times it encircles the point minus 1 is the number of poles I have in the right half. And if it doesn't, it means that I don't have the right half plane poles. In other words, I'm stable. And this is called the Nyquist Criterion. And this is a derivation that doesn't use the integral. So here is basically how it works. So let's go back to that system that we have. This guy. And let's see what happens if you apply the Nyquist criterion to it. So the good thing about Nyquist criterion is that basically the same data that you use to determine the Bode plot can be, it's a different plot, it's a polar plot of Bode plot. Right? Because this is so basically if you look at the loop gain, here we basically looked at the magnitude and phase of the loop gain and plotted them like that versus frequency. Then in a Nyquist plot, what you're doing, you're plotting it versus as a function of frequency. So let's see how this looks like. So you start from some large positive value here with 0 phase. Then you have negative phase, so you basically go, and your gain starts dropping. So by the time you get to minus 180, in this example, what have you done? Are you above point minus 1 or below? So point minus 1 is here, right? This is the magnitude of, or not, well, this is the magnitude of what? This is unity magnitude. So the magnitude is greater than unity. So I'm out here. And then when I come back, by the time I get to more than minus 180, and then I come back down to 180, but am I still on this side or that side? I'm still on this side, right? Because the gain is greater than 1, the magnitude of the gain. So it's farther out. So I'm going like that, and then I go like this. Right? Do you see how these two are the same thing? No. Okay, let's go over it. So here, at very low frequencies, what is the magnitude? Some T0, right? And what's the phase? 0. Then I go and as I increase the frequency, what happens? My gain drops, which means that I'm getting closer to the origin. Right, so maybe just make this a little bit nice. Like that. So this radius, R, is reducing. This is R. This is theta. Right? In a polar coordinate. And now at this point, for instance, when you get to minus 90 degrees, where is that point? It's here, right? Minus 90 degrees of angle and some magnitude, right? So I get to minus 180, which is here. The first time I get to minus 180. My magnitude is still greater than 1, which means that I will be farther out. R is greater than 1. Correct? Then my phase goes beyond minus 180. Right? This is 0, minus 90, minus 180, more than 180, or less than minus 180, I guess. And then the amplitude is constantly dropping. So it's getting closer and closer. R is becoming smaller. And then it goes back to minus 180. But at this point, still the gain is greater than unity, the magnitude. So it will be farther out here. These were the 2 points that these are these 2 points. This is the polar representation of that. And then you come back, and eventually your angle is 90 degrees, asymptotically. And your magnitude goes to 0 at infinity. This is F, this is omega at infinity. Okay? So I'm evaluating this on the j omega axis because that's what my contour is. So this is basically imaginary of the t of j omega, and this is the real of the t of j omega.
Except for in this case, did you consider minus sign in the definition?
No. We are talking about t. Right? We are interested because we were evaluating 1 plus t of s.
Yeah.
That minus sign is already there.
Okay.
Because for this to become 0, it has to be minus 1. Right? So the way we define it is 1 plus t. And that's why this is like minus 1. So now, based on the criterion, did we encircle? Did we go around, did we encircle point minus 1? We didn't, right? We missed it. You didn't go around it. You just like, so if the one easy way to see is that if I'm sitting at the origin, do I go do 2 pi or not? Or how many 2 pi's I do? So if I start from here pointing to that point, I'm a vector pointing to this point. As it moves, I'm doing this, I'm running back here. I didn't do this. And let me show you an example where you do that. So now if I lower my feedback, my overall loop gain, what does it mean? It means that just the whole thing's shrunk, right? This whole curve is shrunk. I can scale it down by some constant, right? Which is like controlled by the RF. Now if I shrink it, what happens is that it becomes smaller, and I can shrink it so that, right? The whole thing, well, it would just scale down version of that. Didn't do a great job of drawing it. It's nice, but something like that. You see it? Now am I circling it or not? I am, right? Because see? Oh, I'm sorry. You have to do it from point minus 1, not from origin. So here. I did 1 encirclement, right?
Around.
See, if my point minus 1 is my reference, where I start my doing that, right? Look. This is what I do. But here, look at it. So I've encircled it. So this is why at lower gain, at lower feedback, I was unstable. But at higher feedback, I got stable because this became very large. And at much lower feedback loop gain, I was still stable. Why? Because basically this is what it did. So this is very low loop gain, larger loop gain where I got unstable, and then even more when I got stable again. And this is called conditionally stable. This system is conditionally stable. Yes, you got the question?
But you haven't drawn the part of the Nyquist plot for the.
I'm sorry, say again?
You haven't drawn the part of the Nyquist plot for negative frequency, right?
Right. No, so
like
basically, I know it's okay. So if I know that the negative. So since I'm going from minus j omega minus infinity to plus it. Okay, so I skipped that part actually. So since my contour is chosen to go from minus infinity j omega sa minus j infinity to plus j infinity, roughly speaking. So I know, and I know all my polynomials here have real coefficients. I know that this part, the upper part of this thing,
problem is in counting the number of encirclements in that case. Would you please draw that one too in
Okay,
the
sure.
upper one? No, in the upper one, please. So here there
So you're
is
starting from
some
here?
encirclements around -1. It seems there is some. If you start from, there's some.
No, let's start
counting.
from here, let's sit here.
Right.
And see how many how many turns we see. Let's just count them. Starting from here. I'm on the black curve still. Still no encirclements, right?
Yes.
0 so far. Then look.
There's one here.
No.
No, but you started from
No,
Just-
no.
what?
No, wait.
Okay.
Let's see how many full 2 pi's I do.
Uh-huh.
Okay? Let's start from here. I'm starting from here. So how many full 2 pi's I've got so far? 0. Okay, so let's continue.
So you're saying in reference to
How many full 2 pi's did I overall?
0.
0.
You're saying in reference to the starting point.
The reference point is -1. Which is the origin of the original plot.
In reference
shift.
to where you first chose the point.
Yeah, this is basically frequency. It doesn't matter where you start, right?
Exactly. I'm just saying you just gotta keep it. Remember. where
Because
you
this is,
start.
you have to go back to the same points, right?
Yeah.
Doesn't matter, it's the same thing. So now, because of that, because we know that the other half is the same as this thing, we usually draw only the first half of it. They only plot half of it, which basically is equivalent to say that on the contour, I'm only going from here to there, and I'm ignoring this other half.